Okay, we're still doing the module about vector calculus. And I told you this module starts slow. So here's another video, on probably what you think is pretty basic stuff, partial derivatives. Probably not as up to speed as you think you are on this, maybe not. But when we get to second derivatives, you need some help. Let's go through the basics. Here's the definitions of partial derivatives. Why do you need partial derivatives? Well, when your function is a function of more than one variable. Function of just one variable, you just take its plain old derivative. You got a function of, say, 3 variables, x, y, and z. Here's definitions of those partials. Basic calculus stuff. The way you go about taking those derivatives is the same way as you take a regular derivative, where you treat the other variables as constants. We'll do an example in a minute. And here I'm introducing some other notation for partial derivatives. This is the function f with respect, its derivative with respect to x and then x again, or the second derivative of f with respect to x. So this notation means this. And you do that by taking the partial with respect to x of the first partial with respect to x. And here's a case of partial of f with respect to x and y, one each. Here's what it means. And it can mean this. First, you took the partial of f with respect to y, and then you took the partial of that with respect to x. Or you could do it in the other order, and you get the same answer. First, take the partial with respect to x, and then that with respect to y. Here, it's kind of commutative. This thing means the same as that thing. It doesn't matter the order. Here's a kind of straightforward example. It says, show that this function satisfies this relationship. So we just start taking these derivatives. We'll take the second derivative with respect to x and see if it's the same as the second derivative with respect to d squared, except with respect to a squared. So how do you take the derivative of u with respect to x? Well, first you have to take, before you take the second derivative, you have to take the first. And there you just take this, you pretend t is a constant. This will be minus sine. And this will be plus cosine. And then to take the second derivative, you take the derivative of that. So it'll be minus cosine minus sine. Okay? Similarly, when you take it with respect to t, you'll have to bring, you're treating x as constant, right? This is all basic stuff. I know you know this, but I'm going through it once really quick. This will be minus a sine x, and it will be a cosine x, etc. Then you just substitute them in, and you see that yes, indeed, this relationship is satisfied by that function. And all we did was take partial derivatives. No chain rule yet. Now let's get to the chain rule. Why do you even need it? Well, let's say you have a function that's a function of one or more what I'll call primary variables. And then those primary variables are in turn functions of secondary variables. And you're interested in derivatives with respect to those secondary variables. If it's a function of u, say, you want, you know, if you have a variable that's a function of u, and u is in turn is a function of x, and you want the derivative of this guy with respect to x, you can't take the derivative of this with respect to x directly. You have to use the chain rule. You take its derivative with respect to its variable, and then multiply by the derivative of u with respect to x. You have multiple variables. In this case, your original function is a function of both u and v and both u and v are functions of x and y. Partial of f with respect to x is secondary variable. We have to first take the partial of f with respect to u and with respect to v. You'll have as many terms here as you have variables, as you have arguments of the function. So here you have n variables. F is a function of n variables. This partial with respect to just one secondary variable is going to have n terms. These n terms. Partial of f with respect to the first guy times u back to know why there's, oh yeah, each of these u's. Each u is a function of the x. Partial of that particular u with respect to xi, you're taking the overall derivative with respect to. Sorry, I'm not explaining this glibly. You're probably used to it. And if, for example, your secondary variables are a function of just one variable, you can find the total derivative similarly. You still use the chain rule, but you'll end up with the total derivative, because ultimately it's only a function of one variable. I'll do a couple of examples. In another video, I'll do second partial derivatives, and there you better pay attention because it's a lot more difficult. So here we have z is a function of x and y, and in turn, x and y are functions of u and v. Find these two partials with respect to these, I'll still call them secondary variables. So the partial of this guy with respect to u, we're going to have two terms because z is a function of x and y, and I can only take a direct derivative of z with respect to either x or y. Partial of z with respect to x, and then partial x with respect to u, plus the partial of z with respect to y. It's the second primary variable, and then that y with respect to u. Similarly for partial of z. In both cases, I need a dz, or partial of z with respect to x, and a partial of z with respect to y. So between the two of them, I need to find 6 partial derivatives. I need to take 6 partial derivatives. 1, 2, 3, 4, 5, 6. Here I go through that, which is just normal taking a derivative. This is just normal calculus. You'll need to use the product rule. I don't think in quotient rule, there's nothing too much else complicated going on there. I'm not going to go through that. Then when you're all done, you plug them back into this one or the other. Oh, and here's a point. This might look bad because these answers, here's the two answers. It's a function of all 4 variables. You might think that's strange. It seems like it ought to be either all u and v or all x and y. Because we don't want you to cheat. We actually want your answer to be in all 4 variables. Because you could cheat and just say, well, I'll plug this in for x here, this in for y here, and I'll just take the derivatives with respect to u and v the normal way. I don't need a chain rule. That's cheating because you need to know how to do this. So we're going to look for answers in all 4 variables because the only way you could have done that is if you used chain rule. Here's just another case, and it shows, in this case, the total derivative. Your primary function is a function of primary variables u and v. Each of u and v are just functions of the single variable t. So now I can find the total derivative, not just the partial derivative. It's the same kind of thing. D is a function of two variables, so I'm going to have two terms here. Use the chain rule. Take the partials you need to, and I need to take 4 different partials here. 1, 2, 4. I needed to look this up. I don't happen to have it memorized. I think I could take these partials and this partial, derivative here. And anyway, that's the answer. So that's pretty straightforward. You probably remember it from good old calculus. I'm going to save second partials for another video, and this will be much more difficult than you think it is. So see you next video.